For magnetic induction, this is an interesting one. Here's kind of what magnetic induction says, and then I'll show you some diagrams and we'll try to explain what's going on. It says this: an electric current is induced in a conductor whenever the magnetic field the conductor sits in changes in time. Okay, so if you've got a wire, just imagine that there's like a wire here. Okay, that's a conductor. That's a terrible wire, but anyways, here's a wire, and the wire is sitting here. It's got to be kind of connected to something. But if there's a magnetic field that starts changing, okay, so if you've got a magnetic field, a B field that increases, it's getting bigger and bigger, this wire kind of doesn't like that. It's going to actually induce a current. Current is going to flow through this wire. If you've got kind of a loop of wire, so number 2 here, if you can kind of imagine there's like a loop of wire here, if a magnet is moved sort of in and out of a solenoid, that's going to create a current, and if it's moved in and out, it's going to make like an alternating current. Let me show you better. This is the law of electromagnetic induction. Let me show you what Lenz's law says. Okay, so the current induced in a solenoid by changing the B field is directed such that the current produces an opposite magnetic field. Okay, here's what all this says, all these different things. Let's put it all together. Here's what it says. If you've got a loop of wire, so this black loop of wire right here, we've got a loop of wire, and it could be a solenoid. Remember, a solenoid is like a whole bunch of loops, you know, kind of going around and around. So it could be a solenoid. That's typically what we would use. If you take a magnet and move it in, so we're going to move it this way. Remember, a magnet has magnetic field, a B field pointing out. Let me do this so it matches. We've got a B field right here because of the magnet. It points out of the north end of the magnet. As I move this magnet right here, as I move it into this kind of loop of wire, this magnetic field right here is going to increase, pointing in that direction. This loop of wire does not like that. I mean, as much as the loop of wire cares about anything, but I'm going to say it that way. The loop of the wire doesn't like that, and it fights against it. What it does is it actually produces its own current so that it produces a magnetic field. Remember, we have to use right-hand rule number 2. This is for solenoids. And for right-hand rule number 2, it says if your fingers point in the direction of current, your thumb points in the direction of the B field. This B field right here is fighting against this B field. Okay, so as this B field increases, this B field also increases. By doing that, it's going to induce a current that flows around. So again, right-hand rule number 2 says point your thumb in the direction of that B field. Your fingers will wrap around in the direction of the current that flows through here. Okay, so up here at the top it says a current is induced in a solenoid, so a loop of wire, or more likely a whole bunch of loops of wire. A current is induced in the solenoid. It's directed so that this B field right here, the loop's own B field, fights to oppose this increasing magnetic field. So as this magnet is plunged into the loop of wire, it's going to induce a current that goes in this direction, whatever direction that is. I can't tell if it's clockwise or counterclockwise. But once the magnet is in there, okay, so once the magnet is kind of in here, then the loop of wire or the solenoid wants to keep that magnetic field. So if you pull the magnet back out, you're actually removing this B field. Oops. This B field right here. Remember, this B field is pointing that way. This loop of wire now wants to keep that magnetic field. It doesn't like that you're changing it. So as you remove this, you're lowering this magnetic field. This guy now produces that magnetic field because it wants to keep that magnetic field. Again, you point your thumb kind of to the left in this diagram, and that's going to induce current in the other direction. So the solenoid or the loop of wire, or any wire really, but let's say in this case the solenoid wants to keep whatever magnetic field it currently has. So to begin with over here, let's say the loop of wire has no magnetic field. You're introducing a magnetic field to the left. It fights against it by producing a magnetic field to the right. Over here, once the magnet is in there and sitting there for a little while, the solenoid adjusts and says, okay, you forced me to have this magnetic field. I'm going to now keep that magnetic field. Now it's happy with that magnetic field. Now when you remove this magnet, you're removing this magnetic field. It now fights to try to keep its own magnetic field to the left. it produces a current then in the opposite direction. If we take this magnet and we put it in and then take it out, and put it in and take it out, if you do that over and over, what you're going to get is you're going to have a current that is produced in one direction, and then it's produced in the other direction, and then back to the first direction, back to the second direction, and so on. You're going to get an alternating current in your solenoid. Let me get rid of my writing here. Here's a little animation here. If what I'm saying kind of like doesn't make sense to you, check out this animation. Kind of start in around 40 seconds. And you can kind of see it's a little bit dry, but it does describe it fairly well. And that's that.